last class we discussed about the equivalent dynamical system, which gives the equivalent force that are generated in a rigid body while applying force. If you want to solve the number of forces, resultant forces that are acting, which are not able to predict, we can make them as a dynamic model by considering the mass into several masses, maybe 2 masses or 3 masses like that. Okay, it should satisfy 3 conditions. So based on these 3 conditions, we can find out the unknown mass or where we have to place that second mass or first mass like that. So by using that principle, some number of methods available. So one method is Klein's construction, by using which I can find out velocity and acceleration. Okay, so what you did in last class, last semester, you studied about velocity acceleration diagram by drawing the velocity polygon and acceleration polygon, okay, from the space diagram. But here what it says, from the Klein's construction, by using the space diagram itself, we can find out velocity and also acceleration. No need to draw the velocity and acceleration polygon separately. Okay, so that is the main advantage of this Klein's construction. And by using this, we can find out the torque, that is turning moment acting on the crankshaft bearing, that we can predict based on the graphical method. So this can be used as a graphical method to predict or to calculate the turning moment that are generated or that are acting on the crankshaft. Okay, so we have studied Ft. Okay, Ft we have a formula, that is analytical formula we have. So those formula we have considered only the inertia force that are acting on the piston, but we have not considered the inertia force of the connecting rod, inertia force of the crank and all. Okay, so that there are some error in analytical method. So in the graphical method, we considered all those things. Finally, we have calculated, or we can calculate the turning moment. Okay, so for that we need Ft. So that component we can calculate. Okay, so the turning moment that are acting on the crankshaft bearing through Ft you can calculate based on this graphical method. So those 2 things we are going to discuss in this class. Okay, so first we will discuss about the Klein's construction. So for that we should recall the procedure that you obtained to construct velocity and acceleration diagram. Okay, so assume that we have a slider crank mechanism. Okay, so this is a 4-bar mechanism or slider crank mechanism or an IC engine, whatever may be. Okay, so this is an example of a slider crank mechanism. Assume that P is a piston, O is a crank, okay, that is crankshaft, C is a connecting rod, that is a crank pin. So PC is a connecting rod. You know, this is a simple 4-bar mechanism or a simple diagram. Anyone, what will be the velocity diagram? Can you know? How we can obtain the velocity diagram for this? Anyone, can you come and roughly draw this? Yeah, no need to find out any value, numerical value. So what will be the shape? Where we have to start? What is OC? OC is the crank. Okay, so what will be the velocity of the crank? Perpendicular to the link. So that will be acting right angle to the OC. So you have to draw one inclined line. Okay, you have the formula, you can calculate. If omega is given, okay, so suppose if the speed is given, omega you can calculate, multiply by the link length, you can get the velocity value. Okay, what will be the next link? That will be the chain. Okay, so after crank, the force is to be transmitted, or the next link is connecting rod. So connecting rod velocity, where it will be acting? Perpendicular to the connecting rod position. Okay, it may up or it may down. So you have to extend in both the directions. So based on the piston movement, that is the line of stroke, we have to decide which directions we have to draw. So upper side that will go up to infinity, so bottom side only it will intersect because of the line of stroke, so we can get the velocity diagram. Okay, see, is this correct? So this is the velocity of the train. Sorry, this is velocity of the train. Velocity of c with respect to O, fixed point. That should be equal to velocity of the train. So this is the velocity of the connecting rod. Okay, velocity of P with respect to C. And one more thing, velocity of B, that is piston with respect to O, it should be horizontal, that is parallel to line of stroke. So this will be the velocity diagram. Is it correct? So first we have to draw this. Right angle to this, we have to draw one line. It may go up or it may go down. So based on the line of stroke, we have to decide which directions we have to use it. So this we can obtain. Okay. Finally, we can measure by multiplying or by measuring to a suitable scale. We can find out what will be the velocity of this link. What will be the velocity of that are acting on the piston with respect to O, that you can calculate. What will be the acceleration diagram? First one, where it will be acting, acceleration. In acceleration polygon, we have two components. Okay, one is radial component, another one is a tangential component. Radial component always acting parallel to the link. Okay, tangential component will always act perpendicular to the link. One exceptional case, if alpha is given, you can find out tangential component. If alpha is not there, if alpha is negligible, that is angular acceleration of the train, what you can do, you can take the radial component as the acceleration of the particular component. Okay, so here you have to start with the train. So train accelerations is parallel to the link. Okay, parallel to the link. You have to start with the fixed point. It goes from below. Okay, start with because the acceleration point, it is acting downward direction. Okay, so parallel to the link and towards the fixed point. So here O is fixed point, so it is acting downward direction. So there is no tangential component, or assume that the tangential component are negligible. So this radial component itself we can take it as an acceleration. So acceleration of radial component with respect to O, C with respect to O should be equal to acceleration of C. Okay. What will be the acceleration of the connecting rod? There are two components, one is radial and another one is tangential for connecting rod. So the radial component will be acting parallel to the connecting rod. Okay. So this is the radial component. Okay, so that you can calculate if you know the velocity, velocity squared, velocity of PC. So velocity squared of PC with respect to that particular link length. If you put, you can find out the radial component velocity. Okay. This is a tangential component. Okay. Tangential component omega squared into link length. Okay. So alpha into link length that you can calculate. So V squared P. If you know that value, from that you can calculate the tangential component. So according to the scale, you have to draw this. Okay. So at the end point, you have to join. This is the resultant. Okay. So the resultant will be the acceleration of the connecting rod with respect to C. That is acceleration of P with respect to C. And finally, the piston acting along the line of stroke, that is acting horizontal. So the acceleration should be linear. So we have to draw a horizontal line up to point P. So that gives you the acceleration of P with respect to the fixed point O. So that is the final acceleration what we need. Okay. If you want the acceleration at any midpoint or at any point along the connecting rod, Okay, so by using that ratio, we can find out the acceleration, or you can find out the velocity at any point. So this is the one advantage of this graphical method, but we can't use this in analytical method. Okay, so these are all you have learned in last semester itself. Okay, so just we recall this. Any error I made in this? The procedure is correct. You studied now kinematics. You have to tell. Okay. So this is acceleration diagram. So now we are going to discuss about Klein's construction. Without drawing this velocity and acceleration polygon, how we can calculate the acceleration or velocity of a particular link? Either the velocity of the crank, obviously that is given in the problem, or that may be given. So other link, velocity of the connecting rod, velocity of the piston with respect to O, how we can calculate? Again the same thing. Consider again the same 4-bar mechanism. The same velocity polygon is drawn again. Okay, so this will be the velocity polygon based on the given diagram or based on the given data. Okay, if you use the procedure which is adopted for velocity polygon, this you can obtain. Okay, so this is velocity of O with respect to C, velocity of P with respect to O, that is velocity of P with respect to C. Okay, what I am doing here is I am going to turn right angle to this. So the entire diagram is shifted 90 degree. Okay, and it is rotated counterclockwise direction. So how it looks like? Okay, this should be look like. So I am going to rotate this entire diagram to vertical 90 degree. I have rotated. So this VPO component comes here, this velocity of PC comes here, and VCO comes here. Okay. Then what you have to do? You have to extend the connecting rod along the line of the force acting on the connecting rod. Extend that line because the FQ component will be same throughout the connecting rod. Okay. Then from the tank draw one perpendicular line. Both will intersect. So that point is taken as M. Okay, one vertical line is drawn, and from the connecting rod one line is extended. Both are intersected at one point M. So we can get the triangle OCM. Okay. So now look at the triangle OCM. Look at the triangle OC1P1. Is it similar? Is it similar or not? So it is a similar triangle. Okay. So by using the principle, what you can say, the equal or the line having which is parallel or the link which is having parallel, the ratio between equal line, we can use it to find out the unknown value. Okay. So here the link CM divided by C1P1 is equal to the link CO divided by OC1 should be equal to the link OM divided by P1O. So this is a similar triangle principle. The ratio of the similar line or similar link that we can take, that should be equal to a constant. So here the constant may be considered as omega. Okay, so that is equal to omega. That what the Kleins have been derived. So ignore this acceleration diagram. Okay. So OC1 divided by OC, that is from the OC1 is from the velocity polygon. OC is the space diagram, and OP1 divided by OM, C1 P1 divided by CM should be equal to a constant. That constant may be equal to the angular velocity of the crank. So that should be equal to omega. Okay. So now we know what is meant by OC1, that is already calculated from the velocity polygon. So that is velocity of zero. This is velocity of t with respect to O. This is velocity of t with respect to c is omega. So this OC, OM and CM is unknown value, or you can calculate or you can find out from this phase diagram. Now the unknown value is this. Okay, so if VCO is required, what will be the value? VCO is equal to omega into OC. Omega is the constant with respect to rotation of the crank. We can calculate that omega value. VPO is equal to omega into OM, particular link length. Then VPC, that is velocity of t with respect to the point C, fixed point C is equal to omega into CM. Okay. So all the values OC, OM and CM you can calculate from the space diagram itself. If you extend that line OCM from the triangle OCM, you can calculate all the values. Then omega you can calculate from the speed. So all other things you can calculate without drawing the velocity polygon. Clear? So this is the main advantage of having Klein's construction. If you know the space diagram, if you know the principle, so you can calculate by using this formula directly. No need to draw a velocity polygon separately. Okay. Again the same thing for acceleration diagram. This you know. So this is the acceleration diagram for this 4-bar mechanism. So this as usual we use the procedure radial component and tangential component procedure. Okay. Now what I am doing, I know the value Cm. Okay, I extended. So take Cm as radius. I draw one circle. So one circle is drawn there. Okay. So this is the way how you can get the acceleration diagram without drawing this acceleration polygon. And take PC, that is connecting rod as the diameter, draw one more circle. Okay, you know the connecting rod length, take the midpoint and from that midpoint draw one more circle. Okay, clear? Because this is very important. Based on this, you have to draw the graphical method. Okay. By using which you can calculate or you have to calculate the unknown values there. So now take Cm as radius, draw one circle. Take connecting rod length as diameter. Okay, the half of the value as a radius, draw one more circle. So both the circle intersect at one point. Okay, so both red and green has intersected 2 points known. Join those 2 points and extend until the horizontal line OP. Okay, so like this. So this is KL, that is intersection point. Join KL and extend till horizontal line. Okay, so that point may be taken as N. So now what you have to do, join N with C. This point may be this point, this KN intersects the connecting rod at Q. So that point may be taken as Q. Now what you have to do, join C with N. Okay. Now this CQNO is a polygon. Okay. That polygon which gives which will be resembles the shape that you obtained from the acceleration polygon. How? This is a crank. Okay. OC. That OC represents this. Okay, CQ is along the connecting rod. Where the connecting rod, which line is parallel? So this is parallel because radial component of the connecting rod we have drawn. So this C dash X resembles this not CM. This is QC. Okay, and QN which is parallel to this tangential component. Okay, and that QN, sorry, not QN, NO, okay, is parallel to this horizontal line. Okay, so now this 4 acceleration link may be calculated from the polygon CQNO. So now the CN gives the resultant diagram. Okay, so the acceleration of the connecting rod with respect to P. So the acceleration of the piston with respect to C. That gives here this line. Okay, so that is the resultant force of the radial and tangential. Here we have radial and tangential. So for that you draw one line, that is the resultant line. If you draw this CQNO, you can find out all other value. Okay, so again you use the same ratio principle. Okay, O dash C dash divided by OC should be equal to C dash X divided by CQ should be equal to X P dash. Okay, so X P dash divided by that QN should be equal to O dash P dash divided by NO should be equal to a constant. The constant may be omega square. Okay, so we know the omega square, and you know all other unknown values. The up you have a known values. So like this. Okay, so you have a known value, unknown values top, known values you can calculate from the diagram itself. We can get omega squared as a constant there. So again, this is a radial component, tangential, piston with respect to the fixed point. So this is a value you can measure from the polygon itself. So radial component, if you want, you can calculate by multiplying omega square or a constant with respect to OC. So like that, all other unknown value you can calculate. Clear? This is the way to draw the velocity and acceleration polygon without drawing the velocity acceleration diagram. Clear? Any doubt in this? Any doubt in this Klein's construction? Anyhow, we are not going to ask the velocity and acceleration polygon here, because we have studied already. Analytical method and graphical method you have studied. Obviously, this method also should have been taught. Okay, you would have studied this last semester itself. Klein's construction. Okay. Anyhow, if you know the procedure, you can find out velocity acceleration diagram. So that is the main objective of this Klein's construction. But our objective is to find the inertia forces of the connecting rod and inertia forces of the crank. Because inertia forces of the piston we know, but all other inertia force we have not taken in analytical method. Okay, because it is difficult to predict. Okay, because we don't know the connecting rod mass. If we know and where at which point the forces are acting, based on that only we can calculate the inertia force. But in analytical method, it is very difficult to calculate. Okay, so that is the drawback of the analytical method. So that it was mentioned as approximate analytical method. Clear? So now we have to find out inertia force in a reciprocating engine. That is the same construction by using a graphical method. Okay. So why the Klein's construction was explained in detail means that procedure, half of the procedure is to be used here. So that I explained that. So here considering the weight of the connecting rod. So by considering the weight of the connecting rod, then only the inertia force will be acting, because inertia force mass into acceleration. So if you consider the mass, so definitely some inertia force will be acting in the line of stroke or perpendicular to the line. So at which line that is to be acting, that we are going to measure. Again, assume the same 4-bar mechanism. Okay, O, C, P, you have a theta. You know the procedure for Klein's construction, extend the line along the connecting rod. Okay, so that is CN, MO, you know this. Next step, what you have to do, take CM as radius, you have to draw the circle. Because this is very important, this graphical method will be asked in problem. Okay, if the graphical method is asked, you have to draw this in your answer sheet. Okay, so note down the procedure. So you have to take CM as radius, draw the small circle, connecting rod as diameter, draw one big circle. We should passing through P and M. Again the same thing, this is K and L, join KL, extend up to N. Okay, now join C and N. Clear? Up to this is the Klein's construction. The triangle OCN, which gives the velocity polygon, the polygon CQNO, which gives the acceleration polygon. By using which you can calculate the unknown velocity of crank, velocity of the connecting rod, velocity of the piston with respect to connecting rod, velocity of the piston with respect to fixed point, anything you can calculate. So based on this triangle and one polygon. Okay. Then next, what you have to find out? We have to find out the inertia forces that are acting. We know the inertia force Fi that is acting opposite to the piston movement. So this Fi is here. This is Fp. Opposite side you can have Fi. Fi is equal to m into A. That component you know, we have the formula to calculate that. Next, we have to consider the weight of the connecting rod. So that weight will be acting on the center of gravity. Assume that the crank is rotated theta degree. Okay, so the crank, the whole weight is assumed to be acting on the center point. So from G, you know the center of gravity point or the center of the connecting rod. From that point G, you have to draw one line. Okay, so that force will be acting right angle to the connecting rod. Okay, so we have to find out the equivalent mass. Here this is a single mass, M, connecting rod mass we have, because it is a different cross sections, different area and different mass will be cumulatively added in the connecting rod, small I center and big I center. We have to consider this connecting rod as an equivalent dynamical problem. Okay, so last class we discussed, we have to consider the mass into M1 and M2, two separate masses or two mass system. So based on that, you have to calculate M1 and M2 and L1 and L2 you have to calculate. Okay, so the same principle here we are going to adopt. So we know the mass, one mass is placed at the piston. Okay, where the second mass will be concentrated with respect to the connecting rod. To find out the inertia forces, we don't know. It is not placed on the crank pin. Okay, if you place the crank pin, the mass moment of inertia with respect to G will vary, because small I center having a small mass, big I center having a large mass. Okay, so it will vary, so unbalanced force will automatically generate. So this will not give the resultant force. So what we have to do, we have to calculate or we have to consider this as a two mass system. So that point we have to calculate here. So for that I extend the line right angle to the connecting rod. I have to fix a point Z here. Okay, so that point may be taken as Z. So how I can fix the point ZZ? So that should be taken as by using this relation. Let GZ should be equal to K. What is meant by K? K is the radius of gyration. Okay, if you know the mass moment of inertia I, you can calculate K directly. Otherwise, you can consider, you may consider it as a simple pendulum or the compound pendulum problem, by using which you can calculate K. So what we discussed in the previous chapter. So that is two way you can calculate K. So by using the K value, you can find out GZ is equal to K. You can fix this point. So next step, what you have to do, join PZ. Okay, and another one, you have to draw one more line ZD with respect such a way that it should make right angle. So here the angle should be 90 degree. So that is a constraint. So based on which we have to draw that line. Clear? So now this is a point where the second mass is acting. Assume that connecting the rod is having 100 kg. That 100 kg is divided into M1 and M2. That the partial mass is located at distance. Okay. Another partial mass M2 where we have to locate or where it should be concentrated. So that point is D here. So to calculate this D, you have to draw this procedure. Otherwise, we have one more method that we discussed in last class. What is it? How you can calculate the point D? Yes? L1? L1, L2 is equal to kg square. If you know K, you know L1 because P and G is L1. Okay, L2 is unknown value. So K is known. So L1, L2 is equal to kg square. So from that itself we can calculate directly. No need to draw this. Otherwise, draw this right angle triangle and calculate the point D. So now what we have to do? That is, the point is in the connecting rod. We have to find out the equivalent acceleration with respect to D in the polygon, that is CQNO. That is the acceleration diagram as far as concerned. So in that acceleration diagram we have to find out what will be the acceleration of D with respect to O, acceleration of G with respect to O we have to calculate. So for that what you have to do? From G parallel to line of stroke, extend one line till the resultant, that is the small g. From D, draw one parallel line parallel to line of stroke until that resultant, that is your small d. Okay. So now join OG and OD. That gives you the small vector. Okay, OG vector and OD vector. So that gives you the acceleration of G or acceleration of D with respect to the fixed point. Okay, you know the formula, that is OG dash divided by OG. Okay, that is the distance or length is equal to acceleration. So that you can calculate. That is a constant. So omega squared into OG dash should give the acceleration of G with respect to O. The same method. Okay. Now you have extended up to this point. OG you started and OD you have joined. So based on which you can calculate the value, analytical value, by using the acceleration and velocity polygon. Okay. So next step, what we have to do? We have to find out the inertia force which will be acting on the connecting rod. Okay. So now parallel to parallel to OD, from D you have to draw one line. So this is the acceleration. Why we have drawn here? To find out the accelerations which is acting on the point D, we have drawn this. Okay, but actually that accelerating force will be acting along the point D. Okay, so parallel to this OD, you have to draw one line from D till the line of stroke. You have to extend up to this. So this point may be taken as E. Okay, so then the resultant force, because the force that will be concentrated on the center of gravity point G. Okay, so always the resultant force which will be acting through E, that should be parallel to OG. Okay, so what happened? You have to draw one line up to E parallel to OD. From E you have to draw one line, you have to extend. That is the inertia force of the connecting rod which is acting parallel to OG. Okay, with respect to the resultant force which are to be generated in the center of gravity point, parallel to this line, this will be acting. We don't know the magnitude, only the directions we have calculated. Okay, so just extend one line until some distance and left it blank. So that is the direction of inertia force of the conducting rod for this position. If you change the theta, the positions may change with respect to G and D point. Okay. The next thing, so this is the inertia force of the connecting rod. So another one, we have a crank here, okay, OC, that is force acting along the crank pin, FB component, that is the force normal to the crank pin, FB, force acting on the bearing. But we have not considered the inertia force that are acting on the crankshaft. So that inertia force is FR. So where it will be acting opposite side to the crank. So from the crank pin you have to extend that line, one line until maximum. We don't know the magnitude, only we have considered the directions. Okay, so just extend that line. Okay, that is the inertia force of the crank. So this is the inertia force of the connecting rod, that is inertia force of the crank. So this is inertia force of the piston. So based on which you can calculate the torque value. So next what you have to do, you have to find out I in such a way that we know the normal force. The normal force will always acting perpendicular to the piston. So from the piston, draw one line that gives you the normal force, Fn. Okay, so draw one vertical line. So both this fan force and normal force which will intersect at one point. Okay, so that point may be taken as I. So this I is called as an instantaneous center. So based on this you can calculate the moment. Okay, so this is the I point. So now what you have to do, you have already drawn one 10, that is the inertia force. So draw one line which makes a right angle or which makes 90 degree to this line, which will meet the point I. Okay, check this. We have to draw one line which makes 90 degree, okay, so that it meets I and also it crosses X. Okay, and you have to draw one more horizontal line to find out the vertical distance. Okay, you know G point, so you have to draw one vertical line. Why this vertical line is drawn? No? So the connecting rod will always act in downward direction. The mass of the connecting rod, that is W, will be acting here. Okay, if some mass is acting, we should consider or we should find out the inertia force. Some inertia force will be acting in the opposite side because of the mass. Okay, so that component you have to consider. So from G, draw one vertical line. From I, make one horizontal line which resembles the right angle, which gives the 90 degree. So now the entire system is completed. So based on I, you have to take moment about all the forces, Fc into perpendicular distance, xi. Okay, Fr into that perpendicular distance, Fr into that perpendicular distance, Is. So both are 90 degree. Okay, and W with respect to the perpendicular distance, I, Y. We know Fi, we know Fn. So based on which we can calculate all other value. So this is W. So C that is acting at the bottom. Okay, we know Ft, that is right angle to the crank, turning moment, that is acting on the crank, that will be acting as Ft. So these are all the some component. In analytical method we have considered only forces Fq, Ft and Fp. So all other inertia forces are neglected in analytical method. But in graphical we have to consider all those things. Then you have to construct this. So finally you can get this acceleration of the piston, that is the formula you can obtain from Klein's construction. Acceleration of GO, the same principle, omega squared into the link length GO, okay, that gives you in the CQ NO from the acceleration polygon. You can find out this by using Klein's construction. The same point, acceleration of DO, the same you can calculate. What will be the inertia force of the connecting rod? You know the value is mr omega squared. So Fc is equal to, you know the connecting rod mass mc, you know omega squared if the speed of the crank is known, then link length, that is GO, because it is acting parallel to GO. So what will be the force that are acting at G? Equivalent force will be acting at point E but parallel to GO. So you have to consider the link length GO. If you substitute all these three values, you can find out Fc component. So you have to extend that line up to that point. What are all the forces that are acting? Inertia force Fi, normal force Fn, inertia force of the connecting rod Fc, thrust force acting on the crank pin Ft, okay. Inertia force of the crankshaft, that is force acting on the crankshaft bearing Fp, opposite side, that is Fr. So based on these 5 inertia forces, the final turning moment you can calculate. So this is a formula, that is the final turning moment, that is Ft into perpendicular distance, okay. So Ft into with respect to that point, instant radius center, you have to calculate the perpendicular distance because we are taking moment about I, okay. So Ft into perpendicular distance Ic is equal to, first consider the inertia force Fi into perpendicular distance, inertia force of the connecting rod into perpendicular distance, and weight Wc into the perpendicular distance. So based on these three values you can get the final torque, okay. Some cases if you want to consider the inertia forces or inertia force of the crank, that also to be considered. Clear? So this is the value that you have to find out at last, Ft into Ic, that is the turning moment that are generated. So substitute all the value, find out Ft, okay. So Ft into radius, you know the problem radius is given, so finally you have to multiply the radius or the link length, that you can calculate, okay. Any doubt in this?